In the previous video, we had seen this function e to approximate the value of e to the power x. And I had mentioned that the explanation for the curious behavior that we saw is beyond this basic course. Nevertheless, I'm going to show you some peculiar behavior involving doubles that you should be aware of. I'm also going to use this example to introduce you to this very useful concept in C called variable length arrays. So once again, we are calculating the first n terms of this infinite series and adding them up, and that is our approximation to e to the power x. So we can begin by saying if n is negative or 0, then there are no terms to add, so we'll just return 0. So you agree with me that if we ever reach past this if condition, if we ever reach this next line, then we know that n is not less than or equal to 0, which means it is greater than 0. So instead of just calculating these n terms and adding them up in this accumulator variable, I'm going to do something very strange. I'm going to store all the terms in an array. So this is some new syntax. You notice that the size of the array, its length, is n, and that's not a fixed number, right? Its value comes from the caller. So depending on what value the caller gives us, we are declaring an array of that size. And that is why this is called a variable length array. So I'm going to store all the terms in this array, starting with the first term, which we know is 1, because the first term in that infinite series, when I is equal to 0, is x to the power 0 divided by 0 factorial, which is 1. So that's the first term. And now we will calculate the remaining n minus 1 terms using a similar formula to what we saw last time, where the ith term depends on the I minus 1th term times x divided by I. Now last time this was I plus 1, this was I, and the denominator was I plus 1. And since this term here is I, everything is shifted over by 1. So this is actually correct. So far all we have done is calculated all these terms in an array, and now I'm going to add them up. But I'm going to add them up in reverse order. So I'm starting my loop variable I from n minus 1. My condition is as long as I is greater than or equal to 0. And instead of increasing I, plus I, I'm doing minus I, which, as you can guess, decreases I by 1. So we begin with I equal to n minus 1. We'll do the body of the loop. And then just before the end, we will decrease I. And we will continue doing this body as long as I is greater than or equal to 0, which means the last time we do the body is when I is equal to 0. And then we will decrease I to minus 1 and exit the loop. So we're going to process all the elements of the term array in this order, this reverse order, this right to left order. And we're going to do exactly what we did before. We'll add them to this accumulator. Now you might be wondering, why are we doing this? I mean, the answer should be the same whether we add the terms left to right or right to left. Well, let's take a look. So I have encoded this, and now I'm going to compile my code, and I'm going to run it. Now, if you remember, last time when we calculated the sum to 17 terms, we got a very small positive error. But when we tried to calculate to 18 terms, our error became negative. I'm now going to show you that for the revised code, when we calculate the sum to 18 terms, our error is very small. Now it's showing it as 0, but that's only because I'm printing it to 16 digits. There may be some other non-zero digits beyond this which are just not getting printed. But even if I go beyond this, or even well beyond this, so I'm now calculating to 1000 terms, I still have no error, or The error is getting smaller and smaller as expected. And this is even more curious in some sense. Why is it that when we add n terms from left to right, we get an error, but when we add the same terms from right to left, things seem to be working very differently? This is the important point I wanted to make in this video, which is that unlike the properties of real numbers that you're familiar with, associativity and commutativity, when you add real numbers or multiply real numbers, those properties don't hold for double values, meaning the order in which you add or multiply double values matters. You'll get slightly different answers in general if you add up the numbers or multiply the numbers in one order than if you do it in a different order. This is not true for ints, by the way. For ints, it doesn't matter the order in which you add them or the order in which you multiply them. You will get the same answer. Now that answer might be mathematically incorrect because, as we have seen, the calculation can exceed the representable range and then it'll wrap around and so forth. But at least the answer won't change from one ordering of the calculation to the next. But it's very critical to remember that for doubles and also for floats, order of calculation matters, and that is the point I wanted to make in this video. We will now continue discussing loops with more examples involving arrays, starting with the next video.